Morning everyone. I am Dr. K. Ramesh, working as Professor of Mechanical Engineering in the Department of Mechanical Engineering, and this lab, that is Thermal Sciences lab, so is meant for 5th semester Mechanical Engineering students. And here in our laboratory, Thermal Engineering laboratory, so related to thermal sciences, so we are doing experiments on internal combustion engines, and apart from that we are doing experiments on compressors, blowers, and in blowers we have two different types of blowers, that is variable speed and constant speed air blowers. So, and also we have heat transfer laboratory for 6th semester mechanical engineering, and also we have instrumentation engineering. So all these laboratories, so they comprises together, and we call that as a thermal sciences lab. And the students of 5th semester mechanical engineering, so they are doing their thermal sciences, thermal engineering laboratory 1 for in their 5th semester, and moreover in 6th semester they are doing other thermal sciences laboratories. So when you go for this thermal engineering laboratory 1, so we have around 14 experiments. We have around 12 experiments of internal combustion engines. So in this internal combustion engine, so we have wall timing diagram on Anil Engine, then port timing diagram on Textile Engine, then performance and heat balance test on Textile Engine, then performance test on CLM engine, then performance test on Mitsubishi engine, and then performance test on Witty engine, and then performance and heat balance test on Lister engine, and then performance test on single cylinder manual computerized engine, and then performance and heat balance test on single cylinder multi fuel VCR test engine, and then performance and heat balance test on Witty engine, and then we have performance test on reciprocating air compressors, and then performance test on variable speed air blower and constant speed air blower. So these are the experiments which we have in our 5th semester, and around 100% of experiments were covered as per the syllabus given to us. So around 100% of experiments were covered, and especially here, so in internal combustion engines, so all the mechanical engineering students should be thorough with this, with the study of these internal combustion engines. We all know that diesel engine, Rudolf Diesel, so who invented this diesel engine, so a German inventor, he invented this, and initially it runs with peanut oil. So actually it is designed for peanut oil, and later on, so further changes were made in this, and we went for diesel, and in the name of the scientist Rudolf Diesel. So this diesel fuel is itself named after him, and now in our laboratory, so we can go for the first experiment, that is wall timing diagram on Anil Engine. So this engine is Anil Engine, and this is a single cylinder 4-stroke diesel engine, and it has the fuel that is used is high speed diesel here, so which has high calorific value, and this experiment is especially meant to determine the timing of valves. So this we all know that in 4-stroke engine we have valves, and in 2-stroke we have ports, and since this is a 4-stroke engine, so we have valves. So here we are going to find the timing of valves, so with respect to the nearest dead center. Okay, so the actual aim of this experiment itself is to determine the timing of valves with respect to its nearest dead center, and also so what are the things which happens inside the engine. So that is when we have two valves, so one is the inlet valve and other one is the exhaust valve. So in case of inlet valve, when this inlet valve gets opened and when it gets closed, and when we are going to when this especially this exhaust valve opens and this exhaust valve closes. So we are going to see all this in the case of this experiment, that is wall timing diagram on Anil Engine. So apart from this, initially what is the procedure that we have to go do for this experiment is, so we have to go for aim of this experiment, and then what are the equipments or the apparatus which are required to complete this experiment, and we should know about the specification, since we are going to use the speed, the rated speed of this engine in the formulas to determine fuel injection period, valve overlapping period and all. And initially what we have to do here is, so you have to crank the engine. So initially that is the thing. So why we have to go for cranking? So you have to find the order of the strokes. So first, initially what happens? Suction stroke, then compression stroke, then this power stroke or the working stroke, and then exhaust stroke. So we have to find the order of the stroke by cranking, and then we can easily able to identify the direction of rotation of this flywheel. So in which direction we have to rotate this flywheel. So only for that we are going for cranking. So that is, initially you have to do like this, and you can see the movement of this inlet valve and exhaust valve. So here you can see that the exhaust valve, this is the inlet valve and this one is the exhaust valve. This exhaust valve moves down, that means it is going to close. This exhaust valve close. So that is, so when you measure, when you find the top dead center, that is TDC, so and then so you have to the opposite. So the opposite portion is you have to measure, you have to mark a point here. So that is nothing but the bottom dead center. So the TDC and BDC are opposite to each other. That is the movement of the piston. So when the piston reaches the topmost position, that is called as top dead center, and when it reaches the bottommost position, that is called as bottom dead center. So you have to initially you have to mark this TDC and BDC on this flywheel, and then what you have to do, you have to measure the circumference of this flywheel, so that you can find the radius of this flywheel, because we are in need of this radius to determine the angle of event. So that is theta, which is nothing but theta. So theta is an essential factor to determine the what is that the happenings which are in this single cylinder 4-stroke diesel engine. So initially you measure this, you mark this TDC and BDC, and when this TDC, so it starts to move downwards, so we are moving downwards, we can see the exhaust valve close. So the exhaust valve, so you can see that the exhaust valve closes, and then so you can see the in some position, so you can see the movement of this exhaust valve, so upward. So you measure this, okay. So the movement of this exhaust valve, so that is, this is the position at which this valve, that exhaust valve, the position of this exhaust valve opening and closing can be determined by this movement. And similarly, so when you rotate this further, you can see this movement. So you can see the movement of this exhaust valve, and now you can see the movement of this inlet valve. So you can see here, so right, you can see here. So when it reaches from bottom dead center, so this is the place which is bottom dead center, that is opposite to TDC, BDC. So it is bottom dead center which is opposite to TDC. So you can mark all this point, and then you can see the movement of this inlet valve. So the inlet valve, when it pushes downwards, so the inlet valve is pushes down, that means so it allows the atmospheric air inside the engine cylinder. So that means, so initially the pressure inside the engine cylinder is less than that of the atmospheric. So in order to maintain equilibrium, so what happens, so during this cranking or during the movement of this flywheel, so we are allowing the atmospheric air to enter into the engine cylinder. How this will enter into the engine cylinder? So only when this inlet valve opens, so that means, so this inlet valve pushes downwards. So you have to measure this position, and that will be the inlet valve open. So you have to measure all this inlet valve open, IVO. So when this inlet valve move downwards, that is called as inlet valve open. So that means it allows the atmospheric air inside the engine cylinder. So this air, after certain that that air is sucked into this combustion chamber. So that is during the entire stroke is called as suction stroke. So then after that is when the piston moves from the TDC to BDC. So initially the exhaust valve closes, and later on when it reaches the bottom dead center, so the inlet valve also get closes. So then what happens, then the fuel injection, so it sucks the air inside and the compression takes place inside the engine cylinder, and then the fuel injection, before the end of this compression stroke, the fuel injection starts to begin. So when the fuel injection begins, since it is at high compression, so what happens, so that fuel, due to that high compression, it get burns and it starts to produce power. So when it produces power, so it releases that power to the flywheel. So the flywheel it acts as a temporary agent to store the power. So we have to find all this TDC, BDC, inlet valve open, inlet valve close, and then exhaust valve open, exhaust valve close, and then fuel injection begin and fuel injection end. So we can mark all this now. So this is the outline of this experiment. So now you all know where to mark this TDC and where to mark this BDC, and when to mark this exhaust valve close and exhaust valve open, and similarly inlet valve open and inlet valve close. So we all know this. So when you know all this, so you have to convert this radial distance, that is the angular distance, into a linear distance. So only then we can find the value of theta. So only when you know this value of theta, you can find the suction stroke, then compression stroke, then working stroke, that is power stroke, and then exhaust stroke. So we have formulas for all this, so that you can easily measure the suction stroke, compression stroke, and exhaust stroke, and power stroke and exhaust stroke. So this can be find out in order. So that is why initially we did a cranking. So now we can see how we are going to mark all this. So initially we have TDC here. So the opposite side we have BDC. So initially, so you measure this value BDC. In the opposite, it is a bottom dead center, TDC and BDC. So then we can see now the exhaust valve. When you move, so you can see the movement of the exhaust valve here. So you can see the movement of the exhaust valve. So now the exhaust valve EVC, exhaust valve closes. So that is the when the exhaust gases, that is flue gases, so want to comes out of the engine, it pushes the valves outward. So that means when the exhaust valve moves up, so that means the exhaust valve opens EVO. So when it goes down, that is when it is pushed down, that exhaust valve is pushed down, then that is called as exhaust valve close. So you can see that this exhaust valve closes. Then you can see the movement of the exhaust valve here, the movement of exhaust valve. So at one stage you can see it starts to move upwards. You can see now. So now this is the exhaust valve, that is here we have closes and exhaust valve open. So now you can see that the exhaust valve still moves, and now you can see at this stage, so both this there is a movement of exhaust valve and the exhaust valve and inlet valve. So the angle between these two will be called as exhaust valve closes and this inlet valve open. It is called as overlapping period. And now you can see that inlet valve, so it starts to push down. That is the inlet valve. It starts to open, and then so when you further rotate this flywheel, so you can see, so the exhaust valve opens, inlet valve opens, IVO. So this starts to move up, the inlet valve opens. So you have to measure all this. So from the nearest dead center, so if the exhaust valve closes is with TDC, is nearer with TDC, you have to measure this distance with the help of a tape, measuring tape. So this angular distance, you have to convert this angular into linear. So you can find the linear distance, and also you can find the value of theta with this. Then fuel injection. So when the fuel injection starts and when the fuel injection ends. So fuel injection begin and fuel injection ends. So you can see here. So we can see the movement of the fuel at a certain point. You can see now the movement, the fuel rises. So this is the point where this fuel injection begins. So if you want to find how long this exists, so you have to remove the fuel and you can find the movement of the fuel. So as long as the fuel movement continues, so you can say that the fuel injection period occurs. So now it stops. So this is the place where this fuel injection ends. So now you have found out the happenings. So what are they? So they are top dead center, bottom dead center, then when the exhaust valve closes and when it opens, and when the inlet valve opens and when it closes. So if you find all this, then you have to go for a spiral diagram. So with the help of that spiral diagram, so you can go for the valve timing diagram of this particular engine. Okay, so this is the thing about the engine part, and we can go for the calculation separate. So in case of valve timing diagram, so far we have seen how we have to mark readings on the Anil engine, and how we have to measure the circumference of the flywheel, and how we can make this linear distance into angular distance, and we can go for this calculation part. So in case of calculation and tabulation part, so we have to go for the number of events. So what are the events that took place? So for example, inlet valve open. So when this inlet valve open, when it get closed, when exhaust valve open and closed, and when the fuel injection begins and ends. So, and we are going to measure, we have measured the nearest distance from the dead centers. Maybe it may be top dead center or bottom dead center, and we have converted that linear distance into an angular distance, and we have measured the angle with the help of this formula, that is theta is equal to L into this 180 divided by R into pi. So with the help of that, so we have measured some values on the flywheel. So with the help of the measuring tape, and that value we are going to, that is in case of centimeter, we are going to convert that into degrees. And also we are going to measure, we are going to find the different events that occurs. So for example, so this what we can say is a valve overlapping period. So how we can find valve overlapping period? So all those can be measured with the help of the found out with the help of the formulas that were given in the tabulation and calculation part. So now we can go to the tabulation and calculation part. So far we have measured all the values in the engine, and now all those values has to be tabulated as the tabulation given here. So here you can see the events. So what are the events that took place? So inlet valve open, inlet valve close, then fuel injection begin, fuel injection ends, then exhaust valve open and exhaust valve close. So these are the events that were happened, and we have measured all those in the flywheel. And now, so how we have measured all those? So they are measured with respect to the nearest dead centers. For example, when we go for inlet valve open, we can see that it is measured with respect to its nearest dead center, that is top dead center. And when we go for this inlet valve close, it is measured to nearest to its bottom dead center. And when you go for fuel injection begin, this is measured which is nearest to the top dead center, and similarly for fuel injection also. And exhaust valve open, so this is with respect to its nearest dead center, that is bottom dead center. And for this exhaust valve close, it is measured with respect to its nearest dead center, that is top dead center. So we are measuring all this either before the dead center or after the dead center. So when we have measured this inlet valve open, which is before the top dead center, for a linear distance of 4.3 centimeter. So this is the distance from the nearest dead center, it is 4.3. And when you go for, we have to convert that angle, that linear distance into angular distance. So that is converted with respect to the formula. So that is given, so that is angle of event that took place. So that is theta. So that is equal to L into 180 divided by R into pi. So this L is nothing but the angle of event that took place in degree per second. And when you go for this 180, so it is the that you can see here. So that is the normal stroke period. So that 180. And when you go for this R, that is we have measured the circumference of the flywheel, and you have to measure the circumference of the flywheel. So when you measure that, you can easily find the value, that is 2 pi R. So if you, from that you can easily find the value R. So that is taken as R, and pi, you know, that is pi is 22 by 7, that is 3.14. And now we can go for this what is that, the tabulation. And after forming this tabulation, we have to form this what we can say is that is the spiral diagram, or that is with the help of graph. If you draw that, then that is called as spiral diagram. And similar to that, we have to draw the time periods, that is wall timing. The respective diagram is called as wall timing diagram. So when you draw the top dead center and the bottom dead center, in the engine we know we have measured the top dead center, and the opposite part is the bottom dead center. That is the opposite part of the flywheel is the bottom dead center. So we have drawn the TDC and the BDC similar to that of the thing we have measured in the lab. So TDC refers to top dead center and BDC refers to bottom dead center. So now when you are moving the flywheel downwards, so initially we have moved the flywheel downwards. So the exhaust valve, so at the initial stage the exhaust valve so moves downwards, that means the exhaust valve starts to open. So that then on further movement of this flywheel towards the bottom dead center, so then after that movement, so we are moving that flywheel against the gravity, so that is away from the bottom dead center. Then we can see that the inlet valve get close. So we have seen everything in the experiment we have measured, and the inlet valve get close, and on further movement, so you can see that the inlet valve opens and then inlet valve close. So in between that you can see the fuel injection begin and the fuel injection end. So you have to identify the events while you are doing the experiments. So without that we may not able to draw this valve timing diagram. So the sequential order of the events has to be identified particularly while doing the experiments. So if we measure all this, So all the angles were measured using the formula that I have said, and based on that, so you will draw this wall timing diagram. So that is from, you can see the 4 strokes which were which has to be marked on this wall timing diagram. So that is suction, then compression, then power or working, and then the exhaust stroke. So if you pointed out all these events, you can easily draw the diagram if you know the formula. So the first, if you go for the suction period, so the suction period, so it starts from top dead center. So initially it starts from TDC. So then, so we are moving towards further distance. So from TDC, and so up to this, as long as the inlet valve open and when it get closed, so then that period is called as the suction period. So you can see here the distance between TDC and IVC, so that is called as suction period. And compression, and when you go for the compression, so it starts from IVC to TDC. So before the end of this TDC, you have a very high compression. So before the around 22, in case of 4-stroke engines it is around 26 degrees. So before the end of this compression, you have a high compression inside the engine cylinder. So at that time, when you inject the fuel starts to burn. So the fuel injection period, it begins when there is a high compression inside the engine cylinder. So the fuel injection begins. So then, so when it moves, even the inlet valve opens, the fuel injection begins and it moves further. So then after a certain distance, around 4°55' after this top dead center, so you can see the fuel injection ends. Then, so in between that, so the power stroke starts. So even before the fuel injection ends. So from TDC to the exhaust valve open, the power or the working stroke, so enlarges the power or the working stroke. So it continues for a period up to which this exhaust valve opens. Then from the exhaust valve open, so the burnt gases after gaining energy, that is after gaining energy to run the flywheel, so it starts to this fuel, that is the burnt fuel, so it starts to give the power to the flywheel, and the remaining flue gases will be sent out through the exhaust valve. So the exhaust valve opens, and as long as it get closed, then it is called as the exhaust stroke. So far we have seen the tabulation part. So that is, in tabulation, the first 3 column represents the event, position and the distance from the nearest dead center, and the last column, that is the angle, how we can find the angle. So here you can see, so in the calculation part, you can see the angle of event is represented by this formula, that is theta is equal to this L into 180 divided by R into pi. So here this L refers to the circumferential length, and this 180 refers to the normal stroke period, and this R refers to the radius of the flywheel and into pi. So this you can see here, that is for the inlet valve opening. So we have seen in tabulation part, when you go to the tabulation part, you can see that IVO was measured from the nearest dead center, that is top dead center before TDC, of around 4.3 centimeter. That 4.3 centimeter is given as the circumferential length. So that is measured in the flywheel. So that is 4.3 into 180 divided by R is the radius of the flywheel, that is 29.12 centimeter into pi. So here you can get the degree, that is in case of angle, that is 8°27'. So that is the inlet valve open before TDC of around 8°27'. Similarly for this inlet valve close. So that is theta is equal to, so in case of the tabulation, you go to the tabulation and you can see that, so inlet valve closes after BDC of around 11.4 centimeter. So that 11.4 linear distance is taken, and you can find the value, which is 22°25'. So that we can easily represent that the inlet valve closes after BDC of around 22 degree 25 minutes. So we convert this into angular distance so that the spiral diagram or that valve diagram can easily be drawn on that graph, spiral graph, which is given to you. And similarly for exhaust valve open and the exhaust valve close. So the linear distance, for example, if you go for a exhaust valve close, so the before BDC, so you can see that around 26.3 centimeter has been measured in the flywheel. So that 26.3 has to be given here in this formula. Instead of this L, you have to write as 26.3, that is the circumferential length into 180 divided by R into pi. So you will get a value of around 51 degrees before the bottom dead center. And similarly for the exhaust valve close, the same has to be adopted. And when you go for this fuel injection timing, so this is the formula which represents the fuel injection timing. So T into angle between fuel injection period and fuel injection, that is this fuel injection begin and fuel injection ends, that is 360 divided by 360 into speed. So that is T represents to the time, that is 60. So per second, that is 60 minutes. For a minute you have 60 seconds. So that 60 into that angle between FIB and FIE can be measured, and that is 31 degree 28 minutes. So you can write this 360 into the speed is the rated speed of the engine, which is around 650 rpm. So everything is given now, the 60 and 650, this is given in terms of minute. So it is given as 8.06 millisecond, or otherwise you can write as in terms of 10 power minus 3. Milli represents 10 power minus 3. So 8.06 into 10 power minus 3 seconds. So this is the fuel injection timing, that is 8.06 millisecond. Then valve overlapping period. So this is the formula for valve overlapping period. So T into angle between the inlet valve open and the exhaust valve close, divided by 360 into speed. So we know this value. The angle between IVO and IVC has to be taken from this tabulation, and that is around 29 degree 30 minutes. So if you substitute all those, so you will get the overlapping period of 7.56 millisecond. And when you go for the suction stroke, the suction stroke is the you have formula for suction stroke, compression stroke and exhaust stroke. So for suction stroke, it is the sum of normal stroke period, it is around 180 degree. For all the cases, the normal stroke is 180 degree. 180 plus angle between inlet valve open and before TDC, and the sum of angle of inlet valve close after BDC. So when you know all these values, and if you add all those, for example, this angle between IVO, that is inlet valve open before TDC, is around 8 degree 27 minute. So then the normal stroke period is 180 degree, and angle of IVC after BDC is 22 degree 25 minutes. So if you add all those, you will get the suction stroke. So in the valve timing diagram, you can easily draw the graph with the help of this value. And for compression stroke, this is the formula, that is normal stroke period minus angle of this inlet valve close and after BDC. That is, we know this normal stroke period is 180 degree. So minus 22.25 minute, 22 degree to 25 minutes. So you can say that, so when you subtract this, you can find the value of the compression stroke, which is around 157 degree 35 minutes. And when we go for this exhaust stroke, this is the angle of exhaust valve before BDC, and if you add this normal stroke period and the angle of exhaust valve close after TDC, you can find the value of this exhaust stroke. The normal stroke period is 180 degree, and the angle of EVO before BDC is around 51 degree 44 minutes, and the angle of EVC after TDC is around 21 degree 3 minutes. So if you add all this, you will get the exhaust stroke, that is around 250 degree 47 minutes. So when you have to measure the value in the engine, and then you have to give the tabulation with respect to the measurement and that has to be, and all those measurements has to be, that linear distance has to be converted into angular distance, and that has to be drawn in a wall timing diagram, and the same you have to do the calculations. In calculations you have to find overlapping period, fuel injection timing, then suction stroke, compression stroke, and the exhaust stroke. Only if you complete all these terms, so you will get the respective, you can complete the respective experiments. So you have to be thorough with the tabulation, you have to be thorough with how you have to, you can form a wall timing diagram. So with the help of a graph sheet, that is you have to go for a spiral diagram. So you should know how to draw that spiral diagram. So after getting these values, so far we have seen the wall timing diagram and the port timing diagram. So the way in which we are going to measure the events in wall timing and port timing are similar, even though it is similar. So there you have valves, so that is 4-stroke engines, and here you have ports. So you should know the basic difference between a 4-stroke engine and a 2-stroke engine. Measuring the events in wall timing and port timing, and by drawing the wall timing diagram and the port timing diagram, you will be easily able to understand the happenings, what are the things which happens in a wall timing in a 4-stroke engine and in a 2-stroke engine. So the basic difference can easily be identified only by doing experiments on the respective engines. Thank you.